Hi, environmental methodologists. 5 statistical tests for ESM 230. Now, the reason why you're watching this is because one of the things that just makes your faculty really sad is when students get to the upper division like ESM 303 and they're asked to actually do some science, some data gathering and some statistical tests, and they don't know how to do it. And this is really sad. It means that there's been a failure along the way somewhere of your faculty to teach you a not really too difficult concept. It's a mixture of 5 statistical tests, what are the null and alternative hypotheses, how to interpret a p-value. And so here we are. I just want to really pound this into your head. Try to get this stuff into your head, into your long-term recall, so that down the road you don't disgrace me by not being able to do these when you reach your upper division faculty. It's not too bad, and you know that I'm not the most enthusiastic mathematician on the planet, but I do actually find this stuff kind of fun once you understand it and you can play with it in Excel, and I'll try to show you how to do that. So without further ado, here we go. Oh, a note about the background. It's a screenshot from, well, I stole it from the internet, The Ballad of Buster Scruggs, and it's a really horrific movie, which I would not necessarily recommend unless you really like ultra violence, which it is. It's just disturbing. But this scene here shows a fight between gamblers. I can't remember exactly why they were fighting in the movie, but for the purposes of this lecture, it's because this guy here is accusing this guy here of cheating because he's done one of these 5 statistical tests. And so we'll get to that when we get to it later on. Okay, here they are. There's just 5 of these. Memorize what they are, how to use them, and what they do. The t-test, the ANOVA, the f-test, linear regression, which, okay, I'm packing 1, 2, maybe 3 tests into one. That's okay, you won't mind. And the chi-square test. So I'm just going to go through these one by one. But before I do that, note, all of these are tests of data derived from sampling. So just make sure you understand that. These aren't 5 statistical tests you can use for anything. They're only statistical tests you can use to look at data derived from sampling. So this discussion presumes a solid understanding of the principles and limitations of sampling. You should have that. We've covered that pretty extensively in this class. So I'm not going to go over it again, but just these tests refer to data derived from sampling. I feel like I missed something. No. So all of these tests are tests of the null hypothesis. So what is the null hypothesis? You need to know that. And you need to use a specific form of language associated with these. So when someone says, what is the null hypothesis? Actually, when someone says, what is the hypothesis? You should say, what do you mean? The null or the alternative hypothesis. So let's go over what the null hypothesis is. Language goes like this. There's no difference between something and something else. That's how your null hypothesis should almost always be stated. There is no difference between whatever it is you're looking at, usually 2 or more groups. Sometimes there's no association to have that, or there is no association between one variable and another, okay? So you start with there's no difference. Usually what you believe and hope for is the alternative hypothesis, which there is a difference. Like if I'm developing a new pill to cure malaria and I test, have a placebo and my pill, I want there to be a difference between my 2 groups. But the null hypothesis states there is no difference. And I'm not really quite sure why science works that way. I think you should ask a sort of a philosopher of logic. I think it's easier to disprove something than it is to prove something. I think if you try to prove something, there's always alternative possibilities. But once you've disproved something, you've disproven something. So anyway, we start with saying there's no difference, and then we hope to disprove that, and that just leaves one alternative. There is a difference. I think that's how it works in a non-logical philosophical language. Okay, So anyway, so first make sure you get the null hypothesis, you know how to state it and state it properly. There's no difference, no association. And then you run the test, you get a p-value, and that leads to the next problem. How do you interpret the p-value? Well, I hope you watched the lecture on that and you know that now, hope you now know that if the p-value is less than 0.05 or less than 5%, you reject the null hypothesis and you conclude that there is a significant difference between these two groups. Now, the language is super important. This is how statisticians and scientists communicate with each other. Be very careful from now on for the rest of your life in how you use this word significant. That is not a general non-specific word. It's a very specific word with a very specific meaning. It means that you did the statistical test, you got a p-value, and the p-value is less than 0.05. That's all. So you can't say it's kind of significant, a little significant. It's either significant or it's not, and that has a specific meaning in regard to the p-value. Okay, so if the p-value is less than 0.05, you reject the null hypothesis and conclude, yay, that there is a significant difference. My pill worked. That's what you hope. Doesn't always work out that way. I had an ecology grad student, one of my peers in graduate school once. She did some ecology study, and she said she did this test and she got a p-value of 20%, 0.2, and she said, well, that's not significant at the 0.05 level, but that's pretty good for ecology. And she just steamrolled right on, and everyone just sort of went, that is the funniest thing they'd ever heard, and they really respected her just like brushing over that and continuing, and she ended up getting her master's and PhD anyway. Okay, it was funny at the time. Okay, to people who understand what the p-value means and what significance is. That's okay for ecology, you know. Anyway, okay, test number one, here we are. Let's talk about the test. Test number one is the t-test. Make sure you know what the t-test is, and it is a test for whether or not there is a difference between the means of two samples. Got two samples, two different populations you're sampling? Use the t-test. Here's some examples. A group of scientists interested in the liver mass of lake trout sampled from two different watersheds. Okay, got two different watersheds. Get a bunch of trout from this one, bunch of trout from this one, weigh their livers, get the average, ask, is there significant difference between these two means? T-test. Or maybe they're interested in the rate of insomnia experienced between chocolate eaters and coffee drinkers, comparing the average number of hours sleep between the two groups. Interested in the average growth rate of two different grass species used in restoration projects. You see, some of you are eco-resto students, and I'm trying to give you examples of how you might use these statistics in your future work. If you're interested in the average length of time fifth graders spend viewing two different interpretive displays. Some of you guys are interp option people, and so you could do science on your interpretive displays. Or interested in average greenhouse gas emissions per ton of product. That's a mouthful. Greenhouse gas emissions per ton of product of two different plastic manufacturing processes. So your unit's going to be CO2 equivalents per ton, and measure that in two different plastic manufacturing processes. And maybe you can take multiple samples of each process and figure out the greenhouse gas emissions. Do a t-test to compare them. Okay, that's the t-test. So the null hypothesis in the t-test is that there's no difference between the means of the two sampled groups. A p-value of 0.05 allows the researchers to reject that null hypothesis and conclude, therefore, there is a significant difference between these two groups. That's exactly the language you should use. That's the t-test. Test number two, ANOVA, short for analysis of variance. It is exactly like the t-test, but in this case, there are more than two groups, not just two groups, more than two groups. So I just copied and pasted the same language I used before. Liver mass, insomnia, grass species, fifth graders, greenhouse gas emissions, but I made 4 different watersheds. Chocolate eaters, coffee drinkers, and cocaine users. 6 grass species. Okay, more than two groups. use the ANOVA. Pretty straightforward. Got two groups, use a t-test. T stands for 2 maybe? All right, more than 2, ANOVA. The null hypothesis is there is no difference between the means of the groups. A p-value of less than 0.05 allows researchers to reject the null hypothesis and conclude there is a significant difference between all of these groups. Okay, that's the ANOVA. T-test, ANOVA. 2 down, 3 to go. The F-test. This is a little bit funny. The t-test and the ANOVA actually have some underlying assumptions that we will not address in detail here. I'm gonna brush over them. You can get into them if you get to do like really serious statistical stuff. You're gonna have to address these. But I do need to address one, which is the assumption of the t-test and the ANOVA is that the variation between the sampled groups is not different. So also another assumption is that the data is distributed like on a bell curve parametrically. It's normal distribution. That's not always true, and there's a test for that. Don't worry about it. But in the bell curve, if this is the bell curve, the variation might be very little, and so your bell curve goes zoop, zoop, like that. Or the variation might be quite large and go whoop. And it could be that the variation in your two groups is not the same. It might be significantly different. And sometimes you actually have to do that. I think actually when you do your t-test, there's a choice, equal variances or unequal variances. And so to determine that, you can do the F-test. So there's something you're just going to have to learn by rote memorization. The F-test is a test of difference of variation between sampled groups. Okay, there's a statistical test of significance to whether variation is different or not, and that's the F-test. The F-test tests whether the variances between the two groups are equal or not. Okay. And the null hypothesis for the F-test is there's no difference between the variances of the two groups, or not a significant difference. So the p-value of less than 0.05 allows the researchers to reject that null hypothesis and conclude there is a significant difference in the variances between these groups. By the way, I'm going to give you examples of how to do all these tests in Excel at the end soon. Okay, so we got the t-test, we got the ANOVA, we got the F-test, which is a little bit weird. It's not testing difference in means, it's testing difference between the variance, more generally variation, okay, but more specifically the variance. And just so you know, we will not be conducting this test in lab. You might want to, depending upon what you're doing, but I haven't created any exercises for this in the lab. But you do need to know that it exists and what it's for, which means I may test you in an exam on what the F-test is. So know what it is. There's just 5 tests. Include the F-test in there. Okay. The fourth is linear regression, which includes R, R squared, and significance F. So I'm kind of bundling several tests into one. The linear regression, please forgive me. The linear regression, all these things do is they test whether there is an association between two variables. So that's not comparing means. It's looking at the association between variable 1 and variable 2 in a scatter plot, for instance. So for instance, I might be interested in looking at an association between ice cream sales and shark attacks on Long Island, New York beaches. I don't know where I got this one from. I read this somewhere in an example of statistics and correlation and regression. But I don't know if it's true or not, but you might think that as ice cream sales go up, so do shark attacks. That's because, probably, hypothetically, because the more people that are there on the beaches, the more ice cream sales there are going to be, and so there will be more shark attacks. Or more ice cream is sold in summertime because there's more people, and that coincides with shark season. I don't know. So probably not causation, but we're not talking about causation here. We're just looking at linear regression. But there might be an association. Let's measure it. How about cigarette smoking and child birth weight, infant birth weight? Okay, I think that there is an association there, that the more women smoke, the lower on average are the birth weights. Studying grades, is there associated? Is it true that the more you study, the better your grades? Let's do linear regression and find out. You can actually find out how much studying, if you did this right, find out how much studying will get you the grade you want. That would be interesting. Greenhouse gas concentration and atmospheric temperature, a classic climate change thing, which I'm sure atmospheric physicists have been grappling with for decades. How about education, the amount of education you have and lifetime income? How about age and risk-taking behavior? I hear that risk-taking behavior is kind of high in the late teens and early 20s, and then it drops off. So could we do linear regression on that? Sure we could. Okay, back to environmental science. How about between restoration efforts, whatever they may be, like, I know, miles of restoration along a river and salmonid recovery in that river? Okay, so this is all linear regression. Okay, ratio of imagery to text. And I have lots of examples. You can read them yourself. Okay, so now there are two test statistics used with correlation and regression analysis. So you need to know what they are. R is the regression coefficient. That's what its title is, R. And this shows the strength of the association between two variables. So graphically, in a scatter plot, what that means is if all your dots cluster along a line, that's a strong correlation, and R is a measure of that. If you have a line, but the dots are all kind of scattered far away from it, that's a weak correlation. And again, the R value will reflect that. Maybe I explain how that works here. I do. So an R value of 0 means no association. So that would be a scatter plot with a circular blob of points. Okay, you can always do regression analysis or correlation, but the strength of it will vary from case to case. The closer R is to 0, the worse that correlation is. And then it goes all the way up to 1, so it doesn't go very far. It ranges from 0 to 1. 1 means perfect positive correlation, a straight line, which means every single dot falls right on the trend line. So you go from a circular blob of dots to all the dots on a line from 0 to 1. So if you can only go from 0 to 1, then if you're partway, like what's 0.7? 0.7, it's subjective. It's pretty good. How about 0.5? It's okay. How about 0.3? Not so good. Okay? It's not a test of significance. It's not definitive. It's very qualitative. But it communicates to people what you have found. If I say my R value was 8, then that's a pretty strong correlation. Oh, by the way, R can go below 0. It can go to -1. So let's see, from your point of view, this would be a positive correlation. The more of this, the more of this. You can also have a negative correlation. The more you do something, the less you go. Okay, the more drugs you take, the worse your grades. Is that true? I don't know. It's a hypothesis. But anyway, so R ranges from -1 to +1, 0 being no association at all, -1 perfect negative correlation, +1 perfect positive correlation. Okay, so make sure you understand what that means. Now, sometimes, for some reason, I don't understand, statisticians like to square R, so it gets rid of the negative numbers to give you R squared, and I think that's the value that Excel gives you. It gives you the R squared value, which is going to range from, because R can't go over 1, you square 1, you get 1. R squared also ranges from 0 to 1. But it doesn't go negative. Make sure you understand that. So if you have a negative correlation, your R squared value might be 0.8. You have to look at the chart to know whether it's a positive or negative correlation. Okay, let's see. So again, the calculation of R does not yield a p-value. But there is a statistic you can use to get a p-value. To test for the significance of association, there's a thing called a significance F. It works exactly like a p-value. I'll show you how to do it later in Excel. In this case, the null hypothesis is, as usual, there's no significant association between the two variables. A significance F, which is like a p-value, of less than 0.05 0.05, allows researchers to reject the null hypothesis and conclude there is a significant association between these two variables. Okay, I am repeating this phrase again and again in this lecture. I want that phrase to get into your head, into your long-term memory, so that you use this language properly in the future when you do these tests. Okay, so that's where are we? We got the t-test, we got the ANOVA, we got the f-test for variation or variance, and then we got regression correlation, which includes R, R-squared, and the f-test for regression. Cool. Now, let's get to gambling. And why is this guy trying to shoot this guy? Okay, this is where you use the chi-square test. Now, let's assume these guys were playing dice, right? And you're rolling dice, and there's you can get a 1 or 2 or 3 or 4 or 5 or 6. And you expect those things to show up with equal frequencies. But if the dice are loaded, I don't actually know how to play dice and what's good and what's bad. Let's assume that a 1 is good. Snake eyes is 1. So you put a little weight inside the die to make the dice loaded. And when you roll, you get 1s more often than you would expect. Well, it could be that you just get lucky and you just roll snake eyes a bunch. But at some point, you're going to realize something is fishy here and draw a gun and shoot the other guy because he's cheating. Well, hopefully he used statistics to figure this out and not just got drunk and angry, which is probably what happened here. But anyway, what is the statistic? It's the chi-square test, and I'm going to tell you what this is all about. It's not about averages anymore. It's not about looking at the differences between means or associations. It's about this. The chi-square test compares expected frequencies or ratios or fractions or proportions. These are 4 ways of saying pretty much the same thing of categorical variables. So I actually find the chi-square test a little bit intuitively challenging also to teach. One of the things I often do is when I'm starting to figure out what is the statistical test I need to use, and it just doesn't make sense to use the t-test or ANOVA because I'm not actually calculating averages, or I might be, but I'm not comparing 2 populations or 3 populations. It's different. I consider the chi-square test, and usually I come to that. Or you could be smarter than me and just understand and recognize this definition. So here's just some examples of when you would use the chi-square test. Is there a difference in the frequencies of redwoods, Sitka spruce, and Douglas fir trees in forests sampled at different sites? So in this case, like, would you want to do a t-test or an ANOVA? The average number of redwoods, average number of Sitka spruce, and average number of Douglas fir. No, not really. You might want to say, is there a significant difference in the average number of redwoods and Sitka spruce and Douglas fir in a forest, in 2 forests? These are categorical variables that I'm trying to compare: redwood, Sitka spruce, and Doug fir. And I can figure out the frequency of them in forest A and forest B. I wouldn't want to compare the average number of redwoods in one forest to the average number of redwoods in another forest. I mean, I could, but that's a different question. I'm just looking at, is this forest like, it's proportions of trees similar between forests? I'd use a chi-square test. How about this? Is there a different proportion of coho salmon, Chinook salmon, and steelhead in a river before and after it was restored? I might also want to know if there's greater numbers of these fish before and after restoration, but it's a very qualitatively different, well, it's a different question if the proportion of species has changed before and after restoration. How about, do organic and inorganic foods have the same ratio of nutrients? You might say that it has more nutrients or less nutrients, but what about the proportion of nutrients to each other? Chi-square test. Are the different faces in the dice or the different cards coming up at expected frequencies or unexpected frequencies? Chi-square test. Boy, you'd have to be a really smart gambler to do a chi-square test in your head while you're gambling, wouldn't you? So here we go. As usual, the null hypothesis is that there is no difference between observed and expected frequencies. And the the test yields a p-value. If the value is less than 0.05, you reject the null hypothesis. And you conclude that there is a significant difference between the observed and expected frequencies, and then you pull out your gun and no, you don't. We're peaceful here. You work out your differences peacefully. Okay, 5 tests. The t-test, 2 means, ANOVA, more than 2 means, f-test for differences in variance, linear regression, which is the association of 2 variables with each other, and the chi-square that tests frequency of categorical variables. Okay, that's your homework. That's your challenge. Long-term memory in your head. There's going to be tests on it. There's going to be a lab on it. You're going to get it again. You're going to see it again in future classes, probably even if you're not an ESM major. So good for you, right? Good for you, I hope. I hope. Okay, so now I just want to give you some examples of how to do these things in Excel, because you're going to have to do them in a test. Uh-oh, wrong file. 5 statistical tests. Okay, so let's make this bigger for you. How to do this in Excel. I don't actually know what a Mandalorian is, but it sounds like mandarins. I made up these numbers here. I want to know if there's a significant difference between the average number of Mandalorians in each of these places in the galaxy. Whatever. I just put average and standard deviation down below. Now you can see from the average that there seems to be a pretty big difference, but we're going to do a statistical test to see whether or not there is one or not. What would that test be? Oh, you cheated. You look at this. It says t-test, but that is correct. How do you do it? Pretty easy. You go to the data thing here. You should have downloaded the data analysis pack. You look around for something that looks like t-test. T-test. Uh-oh. They offer 3 of them. Paired, 2 sample for means. Just trust me, you don't want that one. No paired. We're not doing paired tests here. 2 sample assuming equal variances and 2 sample assuming unequal variances. Well, do these have equal variance or not? How would you know? You'd run the f-test. If you really cared, you could do the f-test. Alternatively, if you're a person like me, you just do them both. And if they both give you the same answer, then you don't have to, it doesn't matter which is true. Let me show you, let's assume they have equal variances. Okay, so I'm going to do this. Click on it, click OK, and it said, well, what are your variables? Well, it's thinking already for me, and I don't want it to, so I'm going to erase what it gives me. My first group is the mandarins, and my second group is the Mandalorians. And I just click OK. There's some stuff here, but really you don't have to do anything with it. The alpha is the p-value 0.05. It's going to open up a new worksheet, and it did. There it is. And of course, for some reason, it won't open it up big. So I'm opening up. It gives you all this stuff that maybe you learned in Stats 108 and 109, and I forgot all of it. The only thing I care about is the p-value, and really it's this one, the p-value, the 2-tailed p-value. And what is it? Is it below 0.05? It sure is. What do I conclude? I reject the null hypothesis that there's no difference in the means between these 2 groups, which makes sense. Let me tell you why. You know how I got these numbers? I use this cool thing called rand between. Rand between in Excel will return a random number between the 2 values you selected. And so I put this in, and then I dragged it down. So all these numbers are random numbers between 20 and 40. The average should be 30, right? And is the average 30? It's not. It's 29, but it's pretty close. And look, if I put in a number anywhere else and hit enter, it regenerates new random numbers. And so if I keep doing that, watch, I went from 29 to 30 to 30.2 to 29.7 to 32.9. This is random variation just happening. I told you that variation occurs all the time, and it does in the generation of random numbers. So I'm not concerned that these numbers are not varying. What did I do for the Mandalorians? Hit escape. These were random numbers between 30 and 50. So this should have an average of 30. This should have an average of 40. I should get a p-value of less than 0.05 because I know there's a difference between these 2 means. There should definitely be. What if I change this to 25 and 35? I don't know. and then I have to copy that down to everybody. Notice that the mean doesn't change. The variance does change. And let's see if that unfortunately this sheet doesn't update. So I'm just going to delete this and redo my t-test over here. You know what? I know these are unequal variances because I really narrowed down the left one, so I'll just assume unequal variances, and I go, okay, and here's my first range, and what do we expect here? We expect there to be no significant difference because I just narrowed the variance. I didn't change the mean. So let's expect a p-value that's still really tiny, less than 0.05, and did we get it? P-value, yep, still less than 0.05. Cool. All right, I could play some more, but I won't because I want to play later with the next one, which is ANOVA. I am going a little bit fast here because I know you can stop and redo this video, and you will need to do these things for, oh, you know what I'm going to show you quickly how to make a chart. You should know how to make a chart anyway, so I'll do this quickly because I just know that some people have missed that message on how to make a chart in Excel. So the way I really insist is the right way and the best way to do it is to not highlight data. Do not do that. Instead, click somewhere else and insert a blank chart. In this case, I want a bar chart. Here they are, recommended charts right here. I want a bar chart. There's a bunch of them. You can do any one. I do this one because I'm not creative. And I go to come across until you see the chart tools and go to design and look for select data, your best friend in chart making in Excel. Add a series. Don't worry about the name, just for the values. I want this one here. Oh yeah, sorry, cancel. I actually just want the average. I want a bar chart. I don't want each thing that doesn't make any sense to chart these out. I want the two averages charted out. So the first one is going to be, it's weird. This is going to be the first bar. Okay, and now I need a new one, so I add a new series. Boom, there it is. Cool. I noticed, so the other thing routinely in a chart showing average is a routine thing to do is to include error bars. And I had some trouble recently with a student because we put in custom error bars over here. You have to go to more error bar options. Ooh, that's funny. Excel is really weird. Okay, click on the bar I want. Add a chart element. Error bars. More error bar options. Custom error bar. Specify value. And I want to go plus and minus 1 standard deviation. So where are they? Plus that and minus the same thing. I was doing this and this stupid error bar was showing up on both bars. And I only wanted it on this bar because this is the standard deviation associated with this mean. I don't want this over there. And the reason, it took me forever to figure this out, but the reason is because the person who made the chart had not put in two different series. They had just I don't know, highlighted both of them, and so they both popped up. If you do that, then the error bar you specify is applied to both bars. So tip to the wise. So I'm not going to do that for the other one. I could, but I won't. You can see that it's twice as big as that. Interesting. Okay, so we're going to move on to ANOVA. Okay, we've got mandarins, Mandalorians, and mandibles. It doesn't matter what they are. I just made up gibberish. But I've got 3 different groups. I've got 1, 2, 3 different means, and I want to know if they're different or not. Statistically significantly different. Null hypothesis is no significant difference between the means of these 3 groups. How do I do it? I go to data. I do the data analysis. I'm looking for ANOVA now. ANOVA. Uh-oh. So I'm pretty sure you just want this one, single factor, not 2-factor with or without replication. I think this is single factor ANOVA. So I click OK. Why do I think that? I don't know. Check me. You can do it. You took statistics. Maybe I'm doing it wrong, so let me know. I'm going to do single factor ANOVA right now. By the way, this is an example of how you can really mess things up by using ANOVA. You have all these tests, but if you choose the wrong one, you're going to get weird results that no one will ever know. So if you're ever doing this for real, for publication, for instance, you want to make sure you're using the right test and really do your own research to figure that out. I'm going to use single factor ANOVA. Okay, there it is. Input range. In this case, you can scan over all your data, which is pretty cool. They're grouped by columns. This is a group, this is a group, this is a group. And click OK, and boom, it's done. I just love how easy it is to do statistics in Excel. And all you really care about is this p-value right here. Oh, wow, that p-value, is that less than 0.05? Yes. No, it's much greater than 0.05. I cannot reject the null hypothesis. I conclude there's no significant difference between these means. And it turns out that makes sense too because of how I got these numbers. This is ran between 30 and 50. They're all random numbers between 30 and 50. Let's change this guy right here. Let's make it bigger. Ran between 40 and 60, say. Okay, so delete 6. So this group here, oh, no. Yes. Okay. The Mandalorians here have an average value of 49. The other guys are small. Let's redo the ANOVA. This time we're going to expect there is a significant difference between at least one of the means and the other two. So here we go again. ANOVA single factor. Okay. And look, it really remembers what I just did. It did that. So I click OK. And I look at the p-value. Oh, the p-value is super small. 7.29 times 10 to the minus 7. Note that the E in Excel means times 10 raised to the power of, in this case, minus 0.07. In this case, there's a huge significant difference between the means. Okay, so that's ANOVA. Pretty straightforward. Let's do the F-test. Can't remember what I did here. I'm looking at the averages here and the standard deviations. I'm going to guess that I used the same random number generations for each of these two columns. So this is between 30 and 50. This is between 30 and 50. I'm going to do an F-test. I expect no significant difference between the variation between these two groups. Data analysis. I'm looking for an F-test. F-test to sample. Yeah, I got two samples, the Mandarins and the Mandalorians, for variances. That's what I want. Okay, and that's the first range, and the second range is going to be these guys. Okay, do it. And that's this guy here. What's my, I expected a big number, P. Oh, F test. I think I want this F value right here. F is a little bit different, doesn't really yield, I guess it does yield a p-value. It's one tail. You don't want that. I think you want this, the F. So critical F, and that is much bigger than 0.05. So we do not reject the null hypothesis. We do not say we can we can't say there's a significant difference between the two variances. Okay, so they're the same. Let's change it. How do we change variance? Let's make it ran between 35 and 45. Make it narrower. 35, excuse me, 45, and enter, and copy this down, and my standard deviation should get smaller. Yep. So let's do the data analysis again. F-test, and that's that. And it's funny how it does that. These guys. Okay. In this case, we do expect a very small F value, and that would be, we would reject our null hypothesis. And we got a, oh man, it didn't work. Poor K-no. I guess I did something wrong. No, I didn't. Maybe I should be looking at the p-value after all, the one-tail p-value. Huh, I guess so. We'll leave it at that because I don't want to spend time troubleshooting this while I'm on camera. But I bet you that's the value we should be looking at, the 0.02, because there should be a significant difference between the variances. I just made them. All right, let's do correlation and regression. So I'm saying on different planets, the more chlorochondria there are, the more midichlorians you can find. I don't know what these things are, so Star Wars experts, shut up. Leave me alone. I'm just going to say this is variable 1, and I think it's associated with variable 2, but I'm going to explore that first by just doing a chart, by making a chart. So I'm going to insert a scatter plot, a blank one, as one does. Make it bigger for you guys. And then select data. I'm going to add. My X values are going to be the chlorochondria. My Y values are going to be the mitochondrions. Okay. Okay. There they are. Great. Click here. You've done this before, so I'm going really fast. Add a trend line. And when you do that, display the equation on the chart, display the R-squared value on the chart. Boom, man, you're pretty done. Now, an R-squared value of 0.91, what do you think that is? Is that a strong correlation or not? It's a strong correlation. It's obvious from this. There's a strong correlation. There's a big, these are close to the line. It's not like a big blob of data, which would make it next to 0. But let's do a test for significance so we can just talk about whether there's a significant correlation or not, or significant regression. So the way we do that is back to the data thing. Click on data, go to data analysis. In this case, what are we looking for? It's called regression. So I click on regression, click OK, and oh wow, it already knows. Does it know? Not sure if it knows or not. Looks like it does, but I'll just make sure. It's these guys here. I want to know if there's a significant correlation between these two groups of data. Same old stuff. Here it is. Significance F is what you're interested in. This really small times 10 to the negative 6. Yes, there is a significant regression, or you could say a significant correlation between these two variables. Take that to the bank. Okay, almost done here, guys. This is the chi-square test. And in this case, the chi-square, just to remind you, is looking at, always pause because it's hard to explain, looking whether there's a significant difference in the ratio of different categorical data. So for instance, in this case, I have dogs in Arcata and McKinleyville, and I'm going to hypothesize that there's no difference in the frequency of these different breeds in Arcata and McKinleyville. I just made this data up here. I just made up some breeds up here. Excuse me. And I just was checking myself to make sure when I did it, they added up to 100. So in this case, I'm going to be asked to compare an observed frequency to an expected frequency. And what I'm going to do is I'll just choose one of these as the expected frequency and choose the other one as the observed frequency. I think it's okay to do that. I'm not totally sure, but I'm going to go with it and see how it works. So do the data analysis, look for chi-square, which is, oh, it's not even here. Chi-square works differently. You go, it's an equation, equal chi-square, and you have all these different options. And I think that the one we should use is the chi-square test. This one here returns a test for independence, the value from the chi-square distribution, whatever this stuff is. So I'm going to use this one. These are just weird. I'm going to use this one, and it says put in the actual range and the expected range, so observed versus expected. I'm just going to put in one range and then the other one. This is the first one, comma. This is the second one, end parens. Hit enter, boom, and now I'm confused. Oh, right. I get a p-value. We'll call this a p-value. That is not significant. This is not less than 0.05. Let's look at the numbers. 39 versus 30, 21, 19, 8, 9. These numbers are pretty close to each other. So let's screw with it a bit. Let's make Arcata have a lot more shepherds. I have Aussies. I want that up. That's got to come down by 9. We'll bring this down by 9. 12 minus 9 is 3. Yep. And so I just changed the frequencies here, and it turned the chi-square significant. Now it looks like there's a significant difference between the frequency of dogs between Arcata and McKinleyville. Okay, if you're to do this, you should also leave a little label for yourself right there so you know what this value is, and then you can take that to the bank in your lab. Okay, ladies and gentlemen, that took 45 minutes. Again, get those 5 things into your head. Learn how to use them in Excel. You'll be a successful statistician in environmental science. Okay, thanks. Bye-bye.